Okay, so this is time to get started again. So welcome. So I'm very happy to introduce today's Colloquium speaker, Professor Philsang from Seoul University. Let me briefly introduce his data. So he got a PhD in mathematics at Northwest University in 70, under the guidance of Professor Kevin Costello. And after that, he was at Yale and Tsinghua University before he joined Seoul University in 2022. So today he's going to talk about geometric Langlands theory through the lens of QFT quantum theory. So please welcome him.
Okay, thanks a lot for the invitation. So yeah, I'm going to talk about this topic. I figured that this is because this is a colloquium talk. I mainly try to make it more accessible to the audience. So, which is to say that I don't really have too much kind of concrete content, but I'm happy to talk about it if you're interested afterwards. So here's an outline. I want to start with introduction to the Langlands program, why you care, and so on. And then I'm going to discuss geometric counterpart of the program for the Langlands correspondence. And then I'll discuss how it's related to this field of physical mathematics. You can say a few words about what kind of things I did. Okay, so let's begin with a famous problem, which is Fermat's theorem. So this is maybe one of the most famous problems in mathematics. So stated as such, the equation x to the n plus y to the n equals c to the n has no non-trivial integral solution once n is greater than 2. And I think it's reasonable to believe that this equation looks just so random. Like, why don't you have coefficient 2 here, or y to the 2n? You can just make a bunch of infinitely many different variants, and they just look just as random as this one. But as it turns out, somehow this particular form of the equation is important in the sense that it is related to other fundamental objects in mathematics, such as elliptic curves and modular forms. So let's explain that. So what is an elliptic curve? Elliptic curve over rational number q is a solution set to the equation of this particular form. So it's a two-variable equation, x and y, and it is this particular form where these coefficients are rational numbers. So, big question, a fundamental question in number theory is just to study the solution set of this thing in rational numbers. That's called the rational solutions. But it is actually quite a difficult problem. It's one of the most fundamental problems. It's too difficult. So, what can you do in that case? The one thing you can do is that you actually try to find integral solution, but modulo p. In other words, you think of all these coefficients in a sort of element of sigma p, and then try to find the pair of x and y satisfying this equation, modulo p. And then you just count the number and call it solve p. You can kind of guess that the expected number is p. So you are just recording the variation from the expected number, which is p. So the difference would be p minus or p, which I denote by ap of e. So given any elliptic curve defined over rational number, we are trying to find the solutions and then record this ap of e for any p. That's what you can do. So for example, you consider this particular elliptic curve defined as such, and then let's take p to be 5. In that case, we are just trying 25 different kind of the candidates here, starting from 0, 0 to 4, 4. And you can find that 0, 0, both sides would be 0, and 0, 4 also becoming 0, modulo 5, and so on. So you find that there are 4 solutions. In other words, solve 5 is 4. And you can easily convince yourself that you can just do this for any given p. And this is the result. I mean, in the case of p equal 2, you can just see that this is obvious. Like you have like 4 candidates, 0, 0, 0, 1, 1, 0, 1, 1. All of them just give 0 modulo 2. So there are 4 solutions. I'm just saying that you can just do this for any p. For any given p, you can do this. And then you record as prescribed, which is that to compute p minus SOR p. And that's AP. So in the case of 2, we just computed SOR p to be 4. So your AP will be minus 2, which is 2 minus 4. In the same way, SOR 3 is 4, so you'll be getting minus 1. 5, 4, the difference is 1, and so on. Minus 2, 4, minus 2, and so on. But here, I mean, it's not so important for this talk, but it turns out that this elliptic curve is known to have bad behavior at 11, which is to say
Can I
that...
ask one question? Why do you consider this difference?
So somehow the expected number turns out p. Yeah, that's kind of going to be sort of the expected number. So you just record the difference. Right, so I was just going to say that, I mean, this is kind of like a smooth variety defined over Q. Turns out that reduction alone 11, reduction at 11, turns out that's not smooth anymore. So that's what you mean by the bad reduction, which is to say that the number you are going to get here, which you can compute, is irrelevant. So you don't really care about that part. You only care about sort of good primes. That was just kind of the remark for the experts. If you don't know what that means, that's fine. You just understand this algorithm. You can just do this for AP in this manner. Okay. So next thing, that was my brief introduction to elliptic curves. Now time to introduce modular forms. So modular form is just a particular holomorphic function defined on the upper half plane. And it is not just random holomorphic function, it satisfies a particular property regarding the action of SL2C on the upper half plane. Which is to say that given this element of SL2C, you act in the usual way, but somehow we satisfy this particular property which depends on the integer k. And that's what's called the modular form of weight k. So you have this c tau plus d to the k, f tau. That's the condition. And it also satisfies some additional condition, which I will explain a little more soon. So one thing you notice is that in the case when ABCD is like a 1101, you get this periodicity condition, which is to say that you can have this kind of the free expansion. So you just change the variable to set q to be e to the 2 pi I tau, and then f of tau, you'd write it as f of q and find this expansion. And then the coefficient would be just complex number. This growth condition amounts to, in this presentation, just saying that n actually starts from 0. So modular form is just kind of the holomorphic function satisfying this particular presentation. And then, not just random kind of expansion. This should be all related to by this SL2 symmetry. Just because of this kind of definition, we didn't use all the condition there. There must be some additional relation, which I'm not going to write down. But one thing I want you to know is that if you just pick random sequence of Bn, there's no chance that it would actually be giving a modular form. Modular form is kind of this expression where these coefficients of Bn's are satisfying some particular condition coming out of this SL2Z symmetry. Okay, so the famous Taniyama-Shimura conjecture, which is now called the modularity theorem, which is the form of the theorem that's proved by Weinstein and Taylor-Wines for proving Fermat's theorem, and then Breuil, Diamond, Taylor actually proved the more general version, which is that if you are given any elliptic curve, that should be modular. What does that mean? It means that if you have elliptic curve, you can find modular form whose coefficients are given by this AP. If you remember, this AP was just the difference between P and the solution set of P. So it's kind of the mind-blowing, kind of incredible statement. I'm going to say a little more about that. But first of all, I want to say that how it's relevant to Fermat's last theorem, just for historical importance. The fact that modularity theorem implies the FLT was known earlier by the work of Rivet, Frey, and Serre. And the statement is that Riebeck's theorem is saying that if you have solution to this Fermat's theorem, then you define this elliptic curve. It turns out this cannot possibly be modular. But if you kind of contrast these two theorems, you get the result, which is that there's no way that elliptic curve cannot be modular. So every elliptic curve should be modular, and then this cannot be possibly the case. In which case, there cannot be solution to this Fermat's theorem. Right. So this is kind of the basic outline of how Fermat's theorem was proved.
Can I?
Sure.
So the previous example of the elliptic curve was not behaving well when P was equal to 11, so P is not modular?
No. So that's a good point. So I said like almost R prime here. Here almost means that except for that prime 11. Yeah. So I'm going to actually show that particular example in the next slide, just to show kind of what kind of things happening. It's kind of crazy. Right. So what I just said, if there exists a solution to Fermat's equation, then we can construct elliptic curve, which cannot exist. So that's the proof. That's how it goes. Right. So let's get back to this example with the table. The claim is that if modularity theorem is true, which is the case, there should exist a modular form with the coefficients given by the solution of this elliptic curve modulo P. And here's the claim. So -2, -1, -2. I'm saying that this is a modular form. If you look at the coefficients of this Fourier extension, this -2, you can see here. This -1, you can see here. This 1, you can see here. This -2, there. 11, you don't care. 13, you have 4, and so on. It's like a magic. So what I'm saying is that this AP of E, which you can just compute by counting the solution of this equation modular P, which is purely number theory kind of object, somehow you can find this crazy analytic object which has all those informations except for like 11 in this case. And I want to emphasize once again that you should never expect such a thing to be happening to any random sequence AP, right? It's kind of a crazy statement if you think about it. Like solution set of this, like whatever this random equation, cubic equation, somehow is encoded by random analytic function.
How can we find such modular form?
So that's another great question. I mean, like there is a way to do something, but right, there is a way to do that. But it's a little hard to explain.
The question is
How can you actually kind of find the modular form?
the closed form of modular form?
Right.
So what the theorem said, you can write down the modular
That's
form.
right. So actually, if you think about the property of modular forms, and you know these APs, you can find kind of the basically everything because there is a kind of prime factorization, and then these prime factors kind of determine the others. And then like a modularity, that being a modular form is almost determining. But I mean, yeah, one can find it with some formula. This is the essential information, right? And I was just going to say that this you should not expect, should have not expected this to happen, but it just does. And that's a really deep and surprising relation between elliptic curves and modular forms, I would say. Right. And then the Langlands program is somehow proposal on generalization, vast generalization of this picture. So this slide like is like just for, I don't know, for dream. It's not quite so. I mean, I don't really expect people to really understand what's going on here, but there are several different fields in mathematics, notably kind of the harmonic analysis and representation theory, and number theory and algebraic geometry, and they are all related in this kind of under this umbrella. And the claim is that what I discussed as modularity theorem is a relation between modular forms and elliptic curves that can actually be generalized to some sort of equivalence between what is called automatic representation of G and Galois representation of G. Galois representation to G chat. And that's what Langlands correspondence says. And if you just look at this statement, this has input data of number field, which is finite extension of Q, reductive group, which is like a GLN, and its dual group. So there are several different kind of input data, which is generalization, making this part generalization of the one below. And the case we discussed is when F is Q, G and G hat is both GLN with n equal 2. So what I'm saying is that this modularity theorem is basically kind of the special case of 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 the Langlands program. Like it's like not even an exaggeration. It's like really I do mean every single phrase of this special case. But then it's like really that strong to prove most famous problem. So it's kind of the vast program. Right. Now I want to transition to geometric analog. And I should say that somehow the content of this slide and maybe the next is the most technical part of the talk. And it's kind of the, I don't know, if you don't follow anything about this, it's going to be fine. Like I'm going to start a new topic in the next 5-10 minutes. But this part is, I think, needs to be said. So let me do. So there is a famous analogy in mathematics, which is that for the base Rosetta Stone, number field, which is finite extension of the rational number, can be understood as algebraic curve over finite field. And then I didn't actually define what automatic representation is. I mean, it'll take like a whole hour to define. But turns out that in this world, this has a nice description, which is that if you have kind of curve, you can think of the principal G bundles and think of the space of G bundles, modular space of G bundles. That's what I mean by bundle G. And technically speaking, it's a sort of stack or algebraic space. Technically speaking, stack. So you think of FQ points, which is a set, and you can think of the function space. So fun here refers to a function space. So whatever automorphic representations are, you just think of the functions, some sort of function space on this modular space of G bundles. That's one side, right? And if you remember, automorphic representation is just like an object on the one side. Another thing is Galois representation. It is also known that the Galois representation has to do with the pi 1, the fundamental group. In this case, what's called the entire fundamental group. So representation is just a map from the entire fundamental group to G chat. In other words, Langlands correspondence is relation between these two, this fun space and representation of pi 1. And Drinfeldt's idea, which is the beginning of the Langlands program, is that if you actually have an element here, which I call G hat local system, G chat local system, then you can find a function here that corresponds to there. So there is a correspondence between that. That's the claim. That's the first variant. Second variant, which is maybe a little more technical, but the claim is that Grothendieck noted that over finite field, a good way to produce a function is by taking trace of a vector space or sheaf. Because if you have a sheaf or vector bundle, you can think of the fiber, which is vector space, and you have a trace of raw values. That's one way to produce a function. So Grothendieck basically had an idea of promoting a function to a sheaf. And this is what is called the function sheaf correspondence. And then, of course, the natural question is that given this G-chat local system, we want to find a sheaf which does yield such a function. That's kind of the upgrade. So that's the second variant. And the third variant is that, if you get algebraic curve over FQ, why don't you go further? Consider algebraic curve over complex number point, like a Riemann surface. The question makes sense there. And in this setting, if you think about this, all these statements were set theoretical correspondence. Like given a Galois representation, there is a harmonic representation, and vice versa, and so on. But in this case, the geometric setup is just so nice that you can hope for more. That's what I'm saying here. You want to have more than a set theoretical statement. And that's giving this categorical form of geometric Langlands correspondence. So let's see. So the claim is that you want to find some equivalence of categories between something about sheaves on 1G and something about G-check local systems on C. And the idea comes out of these two different things, which is that these sheaves that we consider on the left-hand side can be understood as what is called D modules. And on the right-hand side, this G-check local system, in an algebraic form, you can think of the flat connections. And then you can hope for an equivalence of categories reading as such. So let me read. Modular space of G bundles on C, that's a space. You think of D modules there, differential operators and a module set over here. On the right-hand side, you think of this space, flat G-check, and then you think of the category of sheaves, and you want an equivalence. So that, if you have a sheet there, that corresponds to a skyscraper sheet there, which is really just about a particular local system. Okay, so here is a mnemonic for the statement. Left-hand side, bun G is just a vector bundle, and D module, if you don't know what it is, it's just kind of a vector bundle with a flat connection. So left-hand side, you can just read it as a category of flat bundles on space of vector bundles. Right-hand side, this is category of flat bundles, and quadrilateral sheaves, that's like a vector bundle. So right-hand side is category of vector bundles in a space of flat bundles. So there's this fundamental asymmetry between these two things, where exactly you have this flat. The objective flat is placed in different manner, and that makes this whole business non-trivial. But I would say that I said this is meta conjecture in the best hope, and turns out the best hope is not holding, which is to say that when G is non-abelian, it is known that the conjecture does not hold as root. You can make a kind of modification and so on, but I would say that I would point out that this is not true as root. Okay, so that's the sort of the end of sort of the technical part, which you don't need to understand, but I just wanted to state. A natural question you'd ask is, why do you care about geometric Langlands? I mean, Langlands program, clearly, correlator or whatever is going to be strong enough to prove Fermat's theorem, so you should care, right? But geometric Langlands, so all these different variants, and it's unclear whether that has anything to do with the original problem, which we can all agree to be important. So the claim here is that very difficult problem in number theory may become accessible if you use the language of geometric Langlands. And here are some examples. Go proved what is called the fundamental lemma in the Langlands program using what's called Hitchin vibration, which is an important tool in geometric Langlands. And the development in geometric Langlands has been helpful for that. Philsang 4 used the idea of geometric Langlands and actually the result of geometric Langlands to do something about arithmetic Langlands. And he got the breakthrough prize for that. Peter Schulze, he did like so many other things as well, but he used this idea of geometric Langlands to basically try to set like a new foundation for periodic geometry for some aspects. And Ron Parks used the Schulze's idea even further to completely reshape this local Langlands correspondence. He used the idea of Schulze used the idea of Philsang and Fork used both ideas of Fork and Schulze, and then now it's like a basically new scene. So like new era has begun because of this idea of geometric Langlands put to use for arithmetic Langlands. So I'm just saying this because geometric Langlands has been basically paid off. Sorry. Paid off its debt to the original Langlands program. Okay, so I want to switch here and let's start a new topic, which is about basically physical mathematics. And if you were in my first hour, I talked about this general idea of physical mathematics, and now I want to give an example. So the example I want to give is starting with this purely mathematical subject called the enumerative geometry. The aim of the subject is just count the number of solutions satisfying a particular condition. So, how many straight lines are there passing two given points on a plane? I mean, it's like almost like axiom in like Euclid kind of the sense. It's like 1. And you can ask like all sorts of variants of this question. And one variant is, I mean, quite complicated. Again, you don't quite need to understand sort of the detail, but you need, I think I just want to give a flavor of this statement. So let me read. How many rational curves of degree d are there on a generic quintix grid? So the flavor here is that there is a geometric constraint, and you want to count something. And essentially, that's kind of all you need to know. And there is a sort of a degree d. So for each d, you can ask a question, and you expect to get a finite answer. That's kind of the basic argument here. But again, for the experts, let me just, for those who understand a little bit of this algebraic geometry, let me say what I mean by this. So quintix manifold, it just means that it is three-dimensional manifold in a complex sense, which is given by solution set of one equation in P4. So there are 4 kind of the independent variables there, and then you think of the solution set for one equation, so you'd be expecting to get a three-dimensional object. And quintic here just means that your equation is of degree 5. And rational curve of degree d just means that you want to find this P1 inside of P4. So P1, if you know these projective things, is denoted by this UV coordinate. But you want to express this P1 inside of P4, so you should be writing it as alpha i's, which is alpha 0 to alpha 4. And then using this UV, you write it down in this manner, and then degree d is used in this particular manner. So, if you have just any random alpha 0 to alpha 4, that will be finding rational curve on P4. But finding a rational curve on X means that you want to find this alpha 0 to alpha 4 such that f of them is 0. You need to satisfy that equation. So you are solving that. So you are trying to find, your variable now is aij, which is, with this I and j. You'd like to find this aij such that this equation is solved. And if you think about it, because f is kind of degree 5 and this is degree d, of course, like this equation is going to be of this particular form. Just because this is kind of the degree 5d equation. Then you have 5d plus 1 relations, because if you want this to be 0 for any uv, of course you want each coefficient to be 0. So you have 5d plus 1 relations, and there are 4 additional kind of relations coming out of the symmetry. So 5d plus 5 variables, 3 parameters, and then you want to kill this 5d plus 5 3 parameters, so that you'd end up with a finite number. So all there is here is that you'd want to get finite number. And this is basic argument that why you'd expect to get finite numbers. And historically, this problem somehow has been pretty important. So Schubert, in 1886, proved that when d equals 1, the number is 2,875. I mean, like a Schubert, if you heard about it, developed the Schubert calculus essentially to kind of prove these sorts of things. And exactly 100 years later, Sheldon Katz proved that N2 is, I'm not even going to try to read it. There's a certain number here. And N3, you get this big number. So you can imagine that whatever this computation is, it's going to get much, much harder as d grows. That's kind of basically the only thing I will need to know. But the surprise is that in the same year, the group of physicists, they found answer for all d at once. This is kind of crazy. You should kind of imagine how these mathematicians must have felt. They've been trying to calculate whatever there are years, and they found this number. And if you think about it, mathematicians are known to be good at finding general patterns and finding answer for every D and so on. But they've been kind of trying to do this one by one. But then this time around, physicists came along and just kind of gave all the answers. And it's kind of crazy. I mean, the story is like even crazier, which is that actually the first time they gave this answer, the answer was not this one. So these physicists claimed all sorts of answer for all D. Mathematicians, this group of people, claimed N3 to be a particular number. They were different. And of course, mathematicians thought that haha, you're wrong, right? The physicists must have been wrong. Turns out, when they actually had did the computation with the aid of computer. Turns out that they had a computer code error. That's why they were wrong. So when they changed their and corrected their error, they actually produced a number which is the same as N3 of this physicists. So it cannot possibly be a coincidence. They predicted a number which is correct when mathematicians sort of couldn't find. And then it's the story is just beginning. Mathematicians, once they know the answers, they can it's much easier to prove. And Giventhal and Liang Yu, they prove this. Physicists gave an answer, but not like proof of any sort. For mathematicians, this is just like black magic. And natural question that should occur to in your mind is that how is that even possible? And this is the sort of the beginning of subject for the mirror symmetry. I mean, Yonggun here is the world expert in this topic. So we want to talk about this mirror symmetry here. The idea here is that physicists actually had a completely different way of thinking of this problem. Curve counting problem that we discussed can be understood as an invariance of some physical theory. So what is called correlation function of quantum field theory. And let's say the labeling of the theory is x, a. But for physicists, somehow they have reason to believe that this x, a is dual to another theory called x check, b. And here, by dual, what I want to say is that they have different descriptions, so they look different, but their invariance or correlation function should be the same. So physicists somehow have this belief, to which mathematicians have nothing to say. Mathematicians think that I have no idea why they believe that, but physicists just believe that. Turns out that this invariance here is much harder than invariance there to compute. So you can just try to compute the invariance on the other side. Okay, once again, the invariance, this curve counting, is something natural to compute from this point of view x, a. It should be same as x check, b, and you compute in terms of x check, b. And then, because the invariance should be the same, this easier computation should be the same as the harder computation. And this is the beginning of the mirror symmetry. Right. And the story is that this kind of, once the context is found, this completely changes the subject. This universal geometry. It kind of enhances the known problem in algebraic geometry, and also kind of related to subjects in simplex geometry as well. And this is just kind of unexpected bridge between these two different fields in pure mathematics. Again, I want to emphasize once again that this problem of counting whatever rational curves, that was formulated way before the physics consideration was there. So it is pure math problem, but somehow once you find a physical context for this particular problem and try to use some black magic idea of physicists, you get answer without proof. And in fact, this part that the story I'm telling you is only the beginning. There is a even better invariant this kind of a theory, which is category of range or boundary conditions. And Konsevich's kind of conjecture in 1994 for the homological symmetry says that this x comma a, there is a great invariant for the Fukaya category there, and x check comma b, there is a great invariant for the coherent shapes on x check. And because they are both invariants, they should be equivalent. That's the flavor. Okay. So you think that like this is too much of digression from like Langlands? How is it related to Langlands program? So to which I will provide this one, which is that Kapusni, a group of physicists, they said that the Langlands program can also be understood in terms of physics. So if you remember, this is the form of the best of conjecture, equivalence between two categories. And Kapusni and Witten, they argue that there is a duality, another duality, not like mirror symmetry, but using that, you can obtain equivalence between these two categories. And this is also kind of a crazy statement because Langlands program is related to kind of the whatever, like number theory and the Fermat's theorem and so on. What this is saying is that, and then like you need to do all these three different variants and so on, and you end up with this kind of crazy looking categorical equivalence statement. The claim is that even if you didn't know anything about number theory or any of the variants, starting from the other end, which is physics, you would have gotten the same statement. That's the claim. So here's a little bit more detail. This, before the 2D theory was labeled by X and A and so on, but 4D theory in this case labeled by group G and element of CP1. And then it is known that this S duality is duality between these two different four-dimensional theories. And given four-dimensional theory, there's a way to produce two-dimensional theory. If you have quantum field theory, space-time is four-manifold. If you just fix to be two-dimensional direction to be complex, kind of Riemann surface C, then you get this kind of four-dimensional thing, and then this is two-dimensional theory. And turns out that this particular equivalence between G0 and G check infinity is becoming equivalence between, in terms of kind of mirror symmetric context. Before I said like XA and X check B, you'd expect particular X, which is cotangent model upon G, and particular X check, which is local system G check.
What is C?
C is a Riemann surface that I fixed here.
But sigma is also Riemann surface?
Right.
Oh.
So that's how you get the four-dimensional space-time anything. Riemann surface or topological surface, which I will clarify kind of soon. The upshot here is that, this is just a slide for the idea of Kapus-Witten. But in summary, what they have said is that somehow there is a duality between this four-dimensional theory, which is becoming duality between this two-dimensional theory, mirror symmetry. And because you have this T star bond G of A, the category equivalence should be Fukaya category of T star bond G. Because you have this one, the category of boundary conditions should be coherent shapes on log G of C. And Fukaya category of T star bond G, it's closely related to D modules or constructive shapes and whatever. And then coherent shapes, quasi-coherent shapes, this is just a matter of category of functional analysis. So you'll be getting some sort of equivalence between these as a form of mirror symmetry. That's the claim. Okay, so now I want to explain sort of the motivation for my work. So what I'm saying here is that this Kapustin-Witten's work is like a completely physics work. If you have ever seen a physics work, like it's kind of the for mathematicians really, it's not understandable. And for like 10 years or something, I think like no mathematicians were trying to understand like their work. Like maybe it's not fair to say like they're not trying. It's just like inaccessible. Mathematicians just couldn't get like make a heads and tails out of it. So in his interview, he said like I feel like he discovered the meaning of light and couldn't explain it. So my motivation is just explain the meaning of life. That's kind of the motivation for my research program in this direction. But second point is a little more serious, which is that these experts in Langlands, they are actually not too excited about this entire business of composite Witten, because Langlands correspondence is actually about algebraic curve or Riemann surface. You know, when I said like a bungee and so on, it is really just about Riemann surface, because it's coming out of like a number theoretic object. You want to capture this algebraic structure. But if you actually look at closely what composite Witten did, it is just about topological surface. So for example, like for Langlands, elliptic curve means all these different things parameterized by, you know, this upper left line, the usual the fundamental domain and so on. But for composite Witten and for Fitch's, elliptic curve just means topological surface, like torus. It's all the same. So you don't see any sort of structure of this algebraic geometry or the complex geometry. So that's actually why Langlands experts didn't really care to understand work of composite Witten. And Drinfeld even said like he said like he just didn't think it's thing to study this. And then, you know, basically my work is develop this frame of physics in such a way that this idea of Langlands can actually be captured. And you know, the idea is that once you find physical context, you can do all sorts of things, and as you'd expect from other examples, you'd be able to produce something new. And that's kind of the direction of research I've been doing, and it's one direction. So I just want to say a few words about what kind of thing I have done. And not surprisingly from the story, I found some new conjectures and proved new theorems. And I would say like all these conjectures and theorems are just like other examples like a mirror symmetry or Figo-Witten theory. It's kind of unimaginable from the perspective of the usual experts in Langlands program. Just like the other examples, I can make sort of a statement which is just hard to imagine. You'd not think to look at such a thing, but because you have additional context of physics, you'll be able to find what's the right question, what's the expected conjecture, and you know, if you have conjecture, you can it's easier to prove. So it's an enrichment of the subject. And another direction, so it's a little hard to explain because I didn't give any kind of detail, but there is an important subject called geometric representation theory, which is to try to understand representation theory using the idea of powerful toolkit of algebraic geometry. And there is an important work of Raman, Finkelman, and Nakajima constructing some particular holomorphic symplectic manifold. And in my work with Justin Hilburn, we found kind of clarification of that work. Again, based on the physics idea, and this is also was completely new. Completely new that actually like this, I named subject to be Raman 3D homological symmetry. So I made this kind of a statement, and based on my statement, Raman and Finkelman actually wrote the lecture notes. And this idea is because of, again, there is a physical context for any of these claims, and in terms of physical theory, they are related. The subject of representation theory and Langlands theory can also be united. There is another sort of direction of research there. And then this can also be further developed, but this part maybe I'm not going to say more. One thing I want to point out is that there is an independent work by Lenzi, Sakelaridis, and Merkatej, who, based on the sort of the analogy, using similar sorts of idea of the physics, they found application to the original Langlands program as well, which is also kind of pretty amazing. Okay, so I want to end the talk just give you the summary, which is that Langlands program is a huge subject, which is really all this exciting stuff. And the Langlands program made the problem somehow easier in a way because you are working in a sort of complex geometry setting, That's like somehow known to be much easier than say number fields or mixed characteristic. But because it's easier setting, you try to understand a little more by trying to come up with a categorical statement. And then this categorical statement actually has been useful for the original arithmetic Langlands program as well. Kapus and Witten's work, they propose that geometry Langlands can be cast in terms of quantum field theory or ideas of quantum field theory. Experts have believed that it is about the topological version of geometry Langlands, but we showed otherwise. And just like any other subject in physical mathematics, using ideas of QFT, you can actually find new structures in geometry Langlands theory in this manner. And then again, because I have this additional context, I can relate this to other subsets in geometry representation theory, and I'm working on furthering this kind of approach. Okay, thanks a lot.
Any questions or comments?
So what kind of things did you add to this, to the topological version?
So the topological version I didn't add.
I mean, you said that there is something other than topological.
Oh, what I meant is, geometry Langlands itself was, geometry Langlands itself is, when I wrote this is not a topological C, it's a Riemann surface. I'm just saying that, so there was no way to realize this as is claimed by geometry Langlands experts starting from physics. Before, it was all topological surface, and developed kind of framework to realize this with Riemann surface. That's
what you mean? You're saying that you're enhancing some this composition and Witten's program.
Right.
So how did you enhance it? That's what my question.
So when you say how though, like what kind of statement am I getting, or?
So you said the composition and Witten's is described on the topological surface.
Right.
But you're saying that composition and Witten's program actually has more than just this. Is that what you're saying? Or
I think what I'm saying is that Kapus and Witten has had a great idea of trying to relate geometry Langlands to physics, but what they have gotten is not quite geometry Langlands. It's version of topological version of geometry Langlands, and I have found like the setting of physics which actually does give geometry Langlands.
Yeah, that's what I'm question. What is the setting? The physical setting.
Oh, so I mean, I didn't say any kind of technical part here. So basically, the idea is that basically kind of the technical point here is that geometry Langlands is completely kind of the algebraic statement, and the framework of physics that has been developed before is in terms of like a differentiable geometry. So basically, the idea is that you need to have a framework, kind of the framework where you have input from differential geometry as well as algebraic geometry to make sense of it.
Okay.
And then I had this idea of using what is called derived algebraic geometry, where topological surface can also be embedded as well as usual object algebraic geometry. And then there, I made kind of the definitions and kind of framework to make sense of what physicists have done using this language.
Okay. Okay.
And then did this. That's the idea.
So you're basically saying you find the setting there. I mean, you're describing this composition and Witten's program in the derived algebraic geometry.
That was the sort of this first one. That's right.
Okay.
And then after that, like I use other physical input to make new statement about pure mathematics.
Do you have also odd realization aside from drum?
Like Berry and Higgs, Berry and Dolbo?
Yeah.
Yes and no. So Dolbo, yes. Dolbo, yes. Somehow, actually, that was a main, another main idea. I realized that I mean, that idea was known to people like Donagi and Pante and like Arrington, but somehow I realized the physical context for Dolbeau geometry Langlands and realized that drum geometry Langlands can be understood as a further twist in the sense of supersymmetric twist, supersymmetric field theory. And then that's how I got this.
So you get this, the CP1 play that low?
Absolutely, yeah.
Oh, okay.
That CP1 is exactly
Yeah.
sort of parameterization. Yes, exactly.
Yeah, so CP1 gives that.
Exactly.
Okay.
Yeah.
The degree thing. But how about like crystalline, that kind of stuff?
Right, that's a great question. So actually, my belief is that Kapusin's witness program is more like ether, and I think what I did is more like crystalline.
Okay.
If you say that Berry geometry Langlands is more like ether, you know, if you think about it, Berry versus ether is like a drum versus crystalline.
Yes.
So, but I don't know how to say this in a sort of number theory setting or like a characteristic setting, just because I don't really know much about that setting. But I expect that this drum geometry Langlands or the kind of framework that I developed should be applied to this crystalline setting as well, if you do things right.
So that means actually there should be kind of motivic geometric Langlands too, which may not be just but
maybe, yeah. That's kind of a little too crazy for me to digest like on the spot. But maybe.
So that the program of this whole people Venkatesh.
It's three. Benzvi is one person, so 3 people.
Yeah, sorry, Benzvi. So there is it really about global original Langnam?
No, it's a kind of the generalization of the original Langlands. It's like
Generalization of
it's a relative Langlands program.
relative Langnam program.
So it's not just about like the Galois holomorphic representation. It's about like the periods of the holomorphic representation and the special values of n functions.
So it has both geometric Langnam and original Langnam in there, in a certain sense? Or? I mean, we should be very serious about studying their papers to understand.
I think so, yeah. I think that's very fair to say. They have. So one thing I should say is that some of the difference between my work and like their work is that I do construct things like starting from physics, whereas for them they use analogy to say what things should be. And then they actually can claim a lot more things. In that sense, they have room to have geometry Langlands as well as arithmetic Langlands. At least, I mean, they have like a big picture dream of what things should be. In that sense, yes.
So are you saying Kapuskin and Newton derived geometric Langlands correspondence using QFT?
So, again, kind of depending on the sense. So, what do you mean? That depends on what you mean by geometry Langlands. So, they found something like geometry Langlands, which is not what was called geometry Langlands correspondence, but they found a version. Now, that statement has been developed to a mathematical statement by Bensby and Nadler. They developed what is called a Berry geometry Langlands program, which is also like a really interesting program. But that's not the same as what was usually called geometry Langlands correspondence, which is what is called the drum geometry Langlands.
What does QFT have anything to do with?
So this slide, which I believe maybe was like not accessible if you don't know about QFT. This idea that these two things should be the same, and so on, and how you get this kind of category. This is like you use a lot of QFT to make sense of this. And to even have an expectation of something of this sort, you need ideas of QFT. That's where you use.
Another question is, you said the group of physicists gave an answer for ND for OD. What do you mean giving an answer? Is it a conjecture or?
Yeah, it's like a conjecture. Like, I mean, it's just numbers, right?
Yeah.
So if you get numbers which are correct, you can say it's like answer, right?
How
Without
do you
proof.
say if they are correct?
No, I said like it's proved by mathematicians in a few years. Given time, Liang Liu Yang actually proved that these conjectures are correct.
But that was after they.
After that,
After.
only because they knew the answer, they were able to prove that. Before that, you know, like even for N3, that was incredibly hard computation, like using computer and so on.
But how can you call it an answer without proof?
I just said like it's a number which is correct, so you can say that it's answer, but if you want, you can just say like conjecture. That's just kind of a linguistic problem. So.
Any other questions or comments? Then let's finish it by giving him a big round.